Now let's summarize the important terms for inference that we've talked about in video 9.1 and introduce one new one. The null hypothesis is what you believe unless the data convinces you otherwise. It's your status quo, your original claim. Nothing has changed. The null hypothesis is always about the population. And we use a subscript of 0 or not for our null hypothesis. So we see this little subscript 0. So when we say the null hypothesis value for a proportion, we call it P naught. The null hypothesis value for a mean is mu naught. So we would say, for example, our null hypothesis would be P is equal to this certain null hypothesis value of P, or mu is equal to this certain null hypothesis value for mu. When we are doing an actual problem, this will be a specific number. Okay, so these will be specific numbers in our hypotheses. Okay, those are specific numbers. But if we're just talking about it in general, we call it the null hypothesis value, and we use that little symbol to recognize that. Now the alternate hypothesis is saying, okay, this is not equal to. Maybe it's less than, maybe it's greater than, maybe it's not equal to. So we have in general two types of tests, what we call the one-sided test or the two-sided test. So in a one-sided test, we're looking for evidence that the population parameter is either greater than or less than the null hypothesis value. So we would say for our alternative hypothesis that P is less than P naught, or P is greater than P naught. For the mean, we would say, for example, mu is less than mu naught, or mu is greater than mu naught. Now the other type of test would be a two-sided test, and we're just looking for evidence that the population parameter is different than the null hypothesis value. We don't know whether or not it would be greater than or less than. We don't really care as long as it's different. So we say, we use a not equal to symbol in this case. So mu is not equal to mu naught. Okay, so that's just kind of the notation that we're going to use for our null and alternate hypothesis. Remember that the alternate hypothesis is what you're trying to find evidence for. Okay, and if you don't find enough evidence for it, then you can't conclude anything. Either we're going to conclude one of these things, or we're going to say, nope, we don't have enough evidence. Okay, now let's talk a little bit more about the p-value. We talked about the p-value as a conditional probability. Oh, actually, I kind of skipped over this part. Remember that there's two possible explanations for an observed sample statistic that is unusually far from the null hypothesis. In other words, something with a small p-value. The null hypothesis is still true and we got an unusual sample just by random chance, or the unusual sample is evidence that the null hypothesis is false. And some of you may be wondering at this time, well, how small or how unusual does something have to be in order to conclude the second one, that we have an evidence that the null hypothesis is false? So we'll talk about that in just a minute, so hold that thought. So right now, let's just look again at the p-value. Here I have a model, a distribution of the sample means. All right, so in other words, this is all a bunch of X bars in here. We've taken lots and lots of samples. We found the sample means. The mean of all the sample means is the population mean. The standard deviation of the sample means is the population standard deviation divided by the square root of n. Okay, so this is a sampling distribution for the sample mean. Over here we have a sampling distribution for the sample proportion. The mean of all the p hats, so this is a bunch of p hats here. The mean of all the p hats is p, and the standard deviation of all the p hats is the square root of p q over n. So we have sampling distributions here. So if we were to plot one single sample on here, so let's say I take one sample and I get a sample mean of x bar, and x bar is this far from mu, which is our population mean. That's not very far. Okay, so we have a fairly short, this is a short distance away. So when it's a short distance away, the p-value associated with that sample x bar is fairly big, because it represents the area under the curve that is to the left or the right of the sample statistic. So in this case, it's to the left of x bar. So since p is a fairly large value, then I don't think that x bar is all that unusual, because, and you can see how that it is very close to mu. So being close to mu makes the p-value bigger because this area under the curve is bigger. We're not going to reject the null hypothesis here. Now here we have a fairly long distance, okay? So this is fairly far away from p, the null hypothesis value for the population proportion p. So p hat's fairly far away. The p-value is fairly small here. So in this case, we have more convincing evidence maybe that p naught is really not the correct population proportion, because my sample statistic is unusually far away from that p naught value. So here we have a large p-value, not strong evidence. So the p-value, remember, is a conditional probability. I keep saying that over and over again because it is so important. It is the probability that you would obtain a sample statistic at least as far from the center of your model as the one you got if the null hypothesis is true, if H naught is true. The smaller the p-value, the more likely we are to reject the null hypothesis. Okay, so I wanted you to see this picture to kind of get a feel for that. Now, what about the significance? What about the idea of how big p needs to be? Well, we want to know, when is it significantly big? So we have something called the significance level, which we've named the Greek letter alpha, the significance level. And the significance level is a threshold for the p-value. Basically, it tells us, whatever we set alpha tells us when we're going to reject the null hypothesis. So let's say we set the alpha level as this percentage right here. And very typically, we say that alpha equals 0.05, but not always. Okay, it could be less, it could be more. That I mentioned right here, it's common to use 5%. So if this area were 5% here under the curve, then we would see what our p-value was, and we would compare. So if the p-value is less than alpha, you would reject the null hypothesis. If the p-value is greater than alpha, we would fail to reject the null hypothesis. Okay, so let's kind of think about this. So let's say we have some p naught, and we get a p hat, and my p hat ends up right here. So p hat, let me write that so it looks a little better. So p hat, if I were to mark where p hat's right here. Well, if p hat is right here, then my p-value would be the area under the curve that is represented by this blue shaded in area. And you can see here that the area shaded in for the p-value is less than the area shaded in for alpha. So we can say that the p-value is less than alpha, which means that p hat is sufficiently far away from p naught that I would reject the null hypothesis. Let me write this so it's actually legible, because it's certainly not right now. P value less than alpha. Okay. Now let's say, and I'll use mu as an example this time, and so let's say I have mu sub 0 and I have some x bar that falls right here. So if x bar is right here, then the p-value associated with x bar would be fairly large, larger than alpha, because the area represented by the p-value is larger than the area represented by alpha. So then here I would fail to reject HO. Here, reject HO. In other words, HO is, I'm going to say my chance explanation, which is the p-value, is too small to be believable, too small to be plausible. So I'm going to say HO is false. HO is false. Now, when I fail to reject the null hypothesis, can I say HO is true? No. I can't say HO is true, however, because it is still plausible with this x bar that HO could be anywhere. All right. This one's far enough away from P that I think P hat's not, or P naught, that P naught's not plausible. But just because X bar is close to mu doesn't mean mu is true, because X bar could be from a completely different population. There could be a completely different population mean over here for which X bar would be plausible. All right. So we'll talk more about that when we get to what's called type 1 and type 2 errors. But hopefully this gives you a little bit better idea of what we do to determine p hat. So anyway, if alpha is 5%, then we're going to reject the null hypothesis anytime that p is less than 5%. We're going to fail to reject the null hypothesis and say we don't have convincing evidence anytime the p-value is greater than 5%. And that's kind of our typical rule of thumb. If you don't know what to use as a rule of thumb, use 5%. Sometimes alpha is specified as being lower than 5% or higher than 5%, depending on how much evidence we think we need to be fully convinced in a given situation. If a great deal of precision is, like life and death is at stake, we're talking about the bolt that holds the wing of an airplane on, and we want to make sure that part is not defective, we might set alpha much lower because we want to make really, really sure we're convinced before we reject null hypothesis and say something else is true. Other times we might not care how often we're convinced. Maybe we're talking about someone's ice cream preference and we really aren't all that concerned about being strictly accurate, and we may set alpha as 10%. So it just depends on the situation how we set alpha.